Hello and welcome to this recorded e-learning on Virtex-6 and Spartan-6 HDL coding techniques, Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the design considerations that most FPGA designers will use to get optimum results. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Virtex-6 or Spartan-6 FPGA. This module provides detailed recommendations about creating effective HDL that will provide high speed and save FPGA resources. If you're an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you build a good design that will use minimal FPGA resources and get good performance. These practices are designed to promote fast and efficient FPGA designs. After completing this module, you'll be able to code your register resources so your design will have fewer control sets and run at a higher system speed. You'll also be able to avoid the most common coding mistakes that reduce device utilization and system speed. And finally, be able to anticipate how your design will map to the register resources that are provided for you within the FPGA. We first want to point out that these are guidelines. They're not rules, so they're not perfect, but we do believe they will very often give you the best result. Now, these suggestions are especially important because Spartan-6 and Virtex-6 have a 6-input lookup table architecture and flip-flops that have some control signal limitations. Previous FPGA architectures have a lot of similarities regarding control signal usage with the flip-flops. So, with careful consideration to the differences between FPGAs, users should be able to apply most of these same suggestions to older FPGA devices. The key is to realize that these tips will allow the implementation tools to group more logic together into slices, which allows greater device utilization and gives the implementation tools the opportunity to find a better parse solution. This is compounded by the fact that often a poorly coded piece of logic creates a timing critical path for a designer to resolve. And often designers waste a great deal of time resynthesizing and repeating a place and route solution over and over in hopes of meeting their timing objective. If you barely get your design to fit inside of the FPGA, the implementation tool's software options may not be as helpful as you'd like. The best solution is to shrink the register and LUT utilization of your design and to port all functionality to the dedicated hardware resources that you possibly can. Now, this may require the designer to employ some clever use of the unused dedicated resources, but the side benefit is that since the dedicated hardware is fixed in silicon, its timing should be faster than you could implement with equivalent logic, that is, with the slice resources. Likewise, the dedicated resources will consume less power than a slice implementation, so plan on trying to use the block RAM for finite state machines and FIFOs, and try to use as much of the DSP slice resources for arithmetic functionality as you can. The easiest way to add some of these resources to your design is through instantiation by creating an optimized component with the core generator. Synthesis tools will try to improve the speed of a design by replicating logic. Logic replication is a synthesis option that allows the synthesis tool to replicate signals that have trouble meeting timing due to a large fan-out. This will generate more registers and can be a problem if you're running out of available resources. So, if you are already synthesizing with this option, you may want to resynthesize with the option off. Ideally, your FPGA should have device utilization around 85% or less. This works well since the tools have space to move the logic around. Often, this is possible when you port some of the design's components to the dedicated hardware that you weren't planning on doing. The key to building a fast design is to build a design that uses fewer limiting resources. In fact, registers can be at a premium. This is because the LUT capabilities have grown to a 6-input LUT functionality. So if the design you're using is migrating from a previous architecture, it has probably been pipelined at some point. So this design will need to be re-optimized, and consequently re-pipelined to build an appropriate pipeline stage for a Virtex-6 or Spartan-6 6-input LUT. This is because the LUT6 is again 40% more efficient than a LUT4, but this won't yield a performance benefit if your design only uses a couple of LUTs with 4 inputs, like a design that would be migrated from a previous architecture might only require. So, right off the bat, keep in mind that you need to pipeline to a lesser degree, and you need to use as much of the dedicated hardware, that is the shift register LUTs, the block RAMs, the DSP slices, etc., as possible to shrink your device utilization of LUTs and registers. Getting these resources properly inferred can help you manage your design size. For example, designers often don't use the shift register LUT in their design. Recall that this resource saves registers from being wasted to balance a pipelined application. Remember that it is important to use the appropriate resource and check that it was inferred properly by your synthesis tool. There are also other reasons inherent in the registers available in the FPGAs that may prevent users from inferring the best resource, specifically the shift register LUT, the block RAM, and the DSP slice resources. Now we'll talk a bit more about how to get these resources best in the part 2 of this HDL coding series. Meeting your device utilization and timing goals can be more difficult if you're not careful about coding properly for the register's control signal limitations. Now, we'll get into control signal management in a moment. Another topic we will discuss is the use of active low control signals. We were all taught at the university to use active low for power savings, but that does not apply to FPGAs, at least in the current architectures. Simply put, active high control signals not only don't save power, but they actually end up using extra logic. We're not going to spend any time discussing synthesis options in this REL, but we do want to remind you that careful use of your synthesis options can unnecessarily increase the size of your design. We recommend careful use of the logic replication options because it can increase the size of your design inappropriately. So be careful about allowing your synthesis tool to modify your design results. In fact, we discuss proper synthesis tool usage and the caveats associated with a lot of synthesis tool features as part of the Designing for Performance course. So you might want to review the course description and consider attending sometime in the near future. It is very important that designers remember to pay attention to the control signals they're inferring. This is especially important because the flip-flops in each slice share all the same control signals. In this case, there are 8 registers per slice. The point being that if you infer lots of different control signals, you can end up wasting flip-flops, since the implementation tools cannot group flip-flops into the same slice if they don't share the same control signals. This means that if there are 2 registers and both use the same clock and reset but different clock enables, then each register is forced to be part of a different control set and cannot be placed in the same slice. If the case arises later that these flip-flops cannot be grouped with other flip-flops with the same control signal sent, then these flip-flops will be isolated in their slices and the remaining flip-flops will go unused. To be specific, control signals are, of course, sets, resets, and clocks, and a control set is a group of control signals that is used for one slice. This is of concern for designs that have several very low fan-out control signals in their design. In fact, more specifically, what we're trying to teach you is to build your design with consideration to sharing as many control signals as possible within your design, and as early in the design flow as possible to plan on minimizing your control signal usage. Most often, designers that build with too many control sets will not recognize they have a problem until much later after they've implemented the design several times. So if you cannot anticipate that you may have too many control signals, keep a lookout after implementation to see if there are many slices that have unused registers. If so, you may have a problem of this nature. Now note that VCC and ground are connected to each unused port, that is the set, the reset, and the clock enable, etc. So if you are not using the set, reset, or clock enable port, that port will be tied either high to VCC or ground. So VCC and ground are also considered control signals and can be factors in preventing flip-flops from being used. Your HDL code and your synthesis tool will decide what your control signals are based on your coding style and some rules regarding control signal usage. First of all, each flip-flop has 4 control ports: data, clock, clock enable, and a set reset port. The clock enable and set reset ports are designed for active high inputs. An active low input can be used but must be inverted with a LUT to operate properly. There is no local inversion for either of the clock enable or the set or reset ports. You also need to know that the set reset port can be programmed as either a set or a reset, but not both. Unlike older architectures, there is not a separate set and separate reset port available on these flip-flops. So if you want both, either the set or the reset functionality will have to be generated from a LUT, and thus be a synchronous set or reset. The set reset port can also be implemented as asynchronous, although this is not as flexible. An asynchronous set reset port cannot be implemented as a LUT input, so your synthesis tool and the implementation tools don't have the ability to map this control signal to a LUT input. You should always remember that clocks and asynchronous sets and resets always get access to the control ports. This is because they cannot be implemented otherwise. Specifically, asynchronous sets resets cannot be implemented as a LUT input, but synchronous set and resets can. And we'll talk a little bit more about this implication a little later. All 8 flip-flops, now note, will share the same control signals. The Xilinx implementation tools, commonly called the place and route tools, take the synthesized design and map the logic to the FPGA resources. In this example, that is simply a gate to LUT exchange. So while you will code in HDL with a gate functionality, it is the synthesis tool's job to build a design netlist that includes Xilinx primitives, that is, LUTs and registers and other dedicated resources. The map program within the implementation tools will then group the resources into slices and group them effectively for speed and maximum device utilization. For the sake of our discussion, it is important for you to remember that the implementation tools will try to group LUTs that have common inputs and flip-flops that have common control signals into the same slice. This assures good performance and high device utilization. It's the cases where designers infer lots of different control signals in their design that prevents the implementation tools from grouping them into the same slice. In this example, we see a clock enable is built with an active low control signal. This forces the synthesis tool to map this to a LUT input, as we see on the right, and then use 2 LUT inputs, because the flip-flop cannot invert the clock enable signal. This may cause an extra LUT to be inferred depending on the logic inferred on the LUT already. Likewise, the lower example shows both synchronous set and reset signals being inferred. Since there is only one set reset port, one of the signals will have to be driven to a LUT input to get the desired behavior. In this case, the synchronous set was chosen to drive a LUT input. I would like to ask you another question that is not shown on the slide, and that question is, what if an asynchronous set was used in the lower example, rather than a synchronous set? Well, the answer is that since asynchronous sets and resets get access to the control port before the synchronous control signals, the asynchronous set would be connected to the flip-flop rather than the synchronous reset, as shown in the diagram. This would then force the synthesis tool to map the synchronous reset to a LUT input. Xilinx recommends designers build with as few control signals as possible because it usually affects the device packing. This, as I mentioned earlier, is because the designers don't understand their device's register resources well enough. So on this slide, we are showing flip-flops with different signal needs. Since these flip-flops don't need the same combination of control signals, they cannot be placed in the same slices for maximum efficiency. But since the lower flip-flops require a synchronous set and a synchronous reset respectively, the designer's synthesis tool or the Xilinx implementation tools can remap the logic to a LUT input rather than a flip-flop control port. This will allow the implementation tools to group the flip-flops into the same slice. Now, by the way, the reduce control sets property for XST synthesis controls this result, but if you don't design with a synchronous set or reset, it won't be used. It is also good to note that the implementation tools automatically look to group LUTs that have common inputs into the same slice. In this example, the tools took two 5-input functions that have the same inputs and then grouped them into the same slice. Just like we saw in the previous example, likewise here, the implementation tools will automatically try to group the shift register LUTs, remember that's the lookup table reprogrammed as a shift register, and it will group them into the same slice when they share the same input signals. So as we mentioned earlier, a control signal is any signal that is connected directly to a flip-flop or a dedicated resource in the FPGA directly. A control set is a group of control signals driving an individual flip-flop or other dedicated resource, such as a block RAM or DSP slice. Managing your unique control sets is helpful to improving your design speed and device utilization. That is because the implementation tools cannot group flip-flops into the same slice if they don't share control signals. Now, we'll go through an example on the next couple of slides. So to elaborate and explain which flip-flops can be grouped, we wanted to demonstrate a couple of scenarios where the use of control signals can allow or prevent the tools from grouping the flip-flops into the same slice. In each of these examples, we're looking at a group of flip-flops with associated control port usage and asking if you think they can be grouped into the same slice. So it's a little bit of a test. So in case number 1, we've got 3 flops. The first with a clock-enabled set and reset, the second with the same set and reset, and the third with just the reset. Our next case, we've got 2 flops. The first with a clock-enabled set and reset, and then the other with a different set signal, but the same reset. And in our third case, we've got the first flop with a clock-enabled set and reset, and then the other flip-flop to have just the same set, but a different reset. In this case, an inverted reset of the first. So, take a second, pause the recording, and note what you think about each case, and try and get an idea of a good answer in your mind before proceeding to the next slide. Well, here are the answers. The first case, recall the situation with the 3 flip-flops. Yes, the tools can pack these flip-flops into the same slice because the control signals all come from the same set. Case number 2, where we had a different set signal but the same reset, no, they can't be grouped because there's 2 different sets cannot be grouped into the same slice. The same is true for clock enables and other control signals. And in our third case, the answer is maybe. If the reset is synchronous, then your synthesis tool should be able to drive the reset to a LUT input and invert the reset signal to get this to work. Note, if the control signal can be implemented as a LUT input in the case of a synchronous set, synchronous reset, or a clock enable, then the tools have much more flexibility to group those flip-flops into the same slice. So, what do you think the lesson is? So let's take a second and review all the control port usage rules we have covered so far. Control signals are the signals that are connected to the actual control ports on your register. Clocks and asynchronous sets and resets always become connected to the flip-flop control ports. That's because they can't be moved to the data path. Clock enables and synchronous sets and resets sometimes become connected to a flip-flop's control ports, and this is decided by the synthesis tool unless you place the appropriate synthesis tool attribute to dictate how that's going to get mapped to the register's control ports. These control signals can be moved to the data path, and as we've seen from a couple examples, this gives you some flexibility and gives the implementation tools a great deal of flexibility. So we do recommend the use of synchronous sets and resets and clock enables. Asynchronous sets and resets have priority access to the control ports over synchronous resets, and this can be sometimes troublesome. For example, if a global asynchronous reset and a local reset are inferred on a single register, the asynchronous reset gets the port on the register, and then the synchronous reset gets the LUT input. Now, there's no coding style or synthesis option that allows the user to control when a LUT will be used in just this case. So tip, clock enables and synchronous sets and resets can be moved to the data path, and we encourage their use. So since these rules are not obvious, it is important to plan your control signal usage. But there are a couple of other things to keep in mind. First, when planning your control signal usage for your flip-flops, keep in mind that the instantiation of cores will also add additional control signals to your design. So try to share these instantiated control signals as well with your HDL code. Also, try to keep in mind that some of the IP you might use may not follow the same recommendations. For example, we've seen cases where active low control signals have been used in IP. So even though your planning may be appropriate, you may still have to plan on some inappropriate control signals still being in your design. So you might have to test that IP. This may not be a big problem, but we do recommend that you build and simulate your IP as soon as possible in the design process, so you can plan on sharing the control signals appropriately. Likewise, if your design is large, plan on evaluating your synthesis results as early in the design flow as possible. This may be necessary since your synthesis tool can also choose how to build a control signal based on how it optimizes your design. This includes the use of physical synthesis tools such as Amplify, global optimization settings, and logic optimization settings. So always take the time to verify your synthesis tool generated the anticipated and appropriate control signals that you expected. And as I mentioned earlier, active low control signals are simply not recommended. This is because the flip-flops do not have local inversion available, and instead inversion requires a LUT input. And keep in mind that designing with active low control signals is an older design practice, so always check what is available in your silicon before designing in an inappropriate signal. Also keep in mind that if you're using an old design and targeting a newer FPGA, older devices sometimes had local inversions supported for all control signals. So when you are instantiating older components or designs into your new device, you should always reevaluate your control signals usage sum. This slide shows exactly the caveats to using active low control signals in a hierarchical design methodology where an older core, older netlist, partition, or hierarchical design methodology is used. So the key is if any components in your design are using active low control signals, they need to be modified. In this case of a hierarchical component, we would recommend resynthesizing the code with the design modification. In the case of a core, we would recommend regenerating the core, and if partitions are being used, the designers should consider resynthesizing and re-implementing the maintained portion of the design. Now, if your design is not going to use a high percentage of the device, usually less than 70%, this will run at modest speed and does not consume much power, then following these guidelines may not be as critical. But if you have the time to build the design properly, which we really encourage everyone to do properly from the beginning, and you're not sure about your device utilization, you should take the time to build the design properly. Now, in case you're not familiar with partitions, they're supported by the Xilinx implementation tools and allow a designer to maintain parts of a place and route solution. This allows the designer to verify and maintain the results. Finally, we want to summarize the design tips we've given you. First of all, a suggestion for faster and smaller designs is, of course, to use the synchronous set reset whenever possible. Use the active high clock enable and an active high set and reset so that no local inverters for the secondary control signals will be required. Try to build your design with as few control signals as possible. This reduces the overall number of control sets and allows the tools to group logic more efficiently so that you use minimal device resources. This will improve your speed and allow you to pack the most logic into the FPGA device as possible. Clocks and asynchronous sets and resets always connect to the control port of the flip-flop. This is probably the 10th time we've mentioned it, and probably at this point you're going, okay, I get it. Asynchronous sets and resets have priority access to the control ports over synchronous sets and resets. And lastly, clock enables and synchronous sets and resets can become control signals, and that flexibility is why we strongly recommend their use. Hello, and welcome to this recorded e-learning on Virtex-6 and Spartan-6 HDL coding techniques, Part 2. This module introduces the design considerations that most FPGA designers will use to get optimum results. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Virtex-6 or Spartan-6 FPGA. This module provides detailed recommendations about creating effective HDL that will provide high speed and save FPGA design resources. If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you build a good design that will use minimal FPGA resources and get good performance. These practices that we're going to discuss are designed to promote fast and efficient FPGA designs. After completing this module, you'll be able to code your design so that you can infer more of the dedicated hardware resources. You also will be able to avoid the most common coding mistakes which will hurt device utilization. And finally, you'll be able to reduce your dependence on global resets by taking advantage of the Global Set Reset Net, commonly called the GSR. If you barely get your design to fit inside the FPGA, the implementation tool's software options may not be as helpful as you'd like. The best solution is to first shrink the register and LUT utilization of your design, and this also implies that you should port all functionality to the dedicated hardware resources that you possibly can. To do this, you'll need to design appropriately for the dedicated hardware resources. This means correctly writing HDL code that will infer the shift register LUT, block RAM, and the DSP slice resources. This module is going to discuss the most common mistakes designers need to avoid in order to infer as much of the dedicated hardware resources as possible. One of the side benefits to following these coding techniques is that your design will use less power. That is because your design's power consumption can be optimized by using more of the dedicated hardware resources rather than using LUTs and registers. It is very important to remember that one of the biggest reasons to use a synchronous reset is that certain dedicated hardware resources simply don't have and don't support an asynchronous reset. For example, to infer the DSP resource will require a synchronous reset to be coded in your HDL. So if the user is going to infer a multiplier, it will have to include a synchronous reset behavior. Unfortunately, synthesis tools cannot infer all possible configurations of the DSP slice, so this will require you in many cases to instantiate the function you want with the core generator. The DSP slice will allow you to build the most useful arithmetic functions such as multipliers, adders, subtractors, multiply and accumulate, counters, including counters with a programmable terminal count, comparators, shifters, large multiplexers, pattern matching functions, and other functionality. Many designs that run out of slices are not fully utilizing their DSP slice resources. Synthesis tools will infer the DSP slice resources from multipliers, but they're not smart enough to infer other functions. You can control synthesis use with attributes, but not if an asynchronous reset is used. Likewise, many customers try to infer the block RAM resources and are disappointed when their synthesis tool does not allow them to build what they want. Well, this is a typical limitation of most synthesis tools, including XST. One of the benefits of using the block RAM is that it has a minimum clock-to-output time when the output register is used. But what designers don't realize is that, like the DSP slice, the block RAM does not allow inference of an asynchronous reset, which of course has bad coding implications if you build with an asynchronous reset. This is because there is simply, again, no asynchronous reset functionality built into the dedicated block RAM resources. So to infer the block RAM's output register functionality, make sure you use a synchronous reset. Just as I mentioned before, using more of the dedicated hardware resources will improve your device utilization and speed of your design, particularly when you consider that most FPGAs have unused block RAMs, and each effectively can implement hundreds, if not thousands, of flip-flops in effective functionality. Frequently, customers will use their block RAMs for many alternative design purposes, such as ROMs, large lookup table functions, for example, such as a sine or a cosine wave generator. But it can also be used for deep shift registers and one of my personal favorites, complex finite state machines, which of course everyone has. We describe some of these applications in the Designing for Performance course. But the key here is to recognize that using the block RAMs for other purposes can free up lots of flip-flops and help you improve your speed as well as improve your power consumption. Also keep in mind that the easiest way to get the block RAM is to build it with a core generator and then instantiate that core into your design. This is very commonly done because most synthesis tools, again, will not infer less obvious block RAM functionality. Another big reason to use synchronous resets is that synthesis and place and route tools are moving towards selectively demoding a synchronous reset from the control port to a LUT input. This will improve your system timing and device utilization. Now, this is advantageous because less timing critical and low fan-out resets can save the reset port for other functionality. This would also allow the mapper to group unrelated logic into the same slice and improve device utilization and speed. Your synthesis tool should be able to do this, but it will depend on your synthesis settings and it may not be on by default. However, XST does use a synchronous reset synthesis option that is on by default. But note that the implementation tools cannot change what has been synthesized. So with whatever synthesis tool you have, its output is what you're going to be placing and routing. In this example, as you can see at the bottom of the slide, a low fan-out reset has been coded into the design's HDL. After it is synthesized, XST has chosen to move it to a LUT input. This could allow the component to be packed with other similar logic into the same slice, that is, logic that uses the same control signals, and this would improve device utilization. Either way, it is added flexibility given to the implementation tools to meet your timing and as a recommended design practice. So keep in mind that this could be the biggest reason to code for a synchronous reset. As mentioned earlier, XST does have the ability to move a synchronous reset to a LUT input rather than connect it directly to the reset port of a register. However, if you don't use XST, your results will vary because not all synthesis tools can do this. A good reason to use synchronous resets is that it is a standard practice of synchronous design techniques. Using synchronous design practices assures that your design won't glitch and greatly improves the reliability of all FPGA designs regardless of which FPGA vendor you choose. Another good reason to use synchronous resets is that they are automatically constrained when users add a period constraint, which is virtually all Xilinx users. What happens is that the period constraint covers the internal delay paths between synchronous elements, and these paths include synchronous sets and resets. For most designers, this makes the FPGA design easier since they have greater assurance that their system's timing report is much more accurate. Synchronous sets and resets do not need any special timing constraints or timing analyzer settings, unlike asynchronous sets and resets. They also do not require any special switches in the timing analyzer for timing analysis to be complete. Synchronous resets are automatically timed and they are inherently more stable. As you may or may not know, asynchronous resets are ignored by the implementation tools. If you use asynchronous resets in your design, you may not know that they can lead to disastrous functionality. Inherently, synchronous resets are much more predictable. Synchronous resets are less susceptible to accidentally missing timing and, of course, race conditions. But the bottom line is that chances are that if you use synchronous resets, your design will have a much greater chance of working right out of the box. This is dependent on the timing analyzer verifying that you are meeting timing and your functional simulation working properly, of course. With asynchronous resets, there is much less uncertainty because there are a lot of things that can go unnoticed because asynchronous sets and resets are not covered by a period constraint and require special path-specific timing constraints to be applied to your design. As I mentioned, if a reset becomes synchronous, the paths become timed when a period constraint is used on the design, which, as I mentioned also, is very frequently the case. In fact, almost all customers use a period constraint. This will increase the number of time paths. Sometimes it will increase those paths dramatically. Why, you ask? Well, on average, the number of timing paths when you use a synchronous reset increases by 5%. Now, this is not wrong, since you want the design's timing analysis to be correct and help with timing verification. The impact is that the implementation tools will now have more paths to place and route to meet timing. This means more work to do and will slightly increase implementation times. But as I said, this is still better than the design not operating at all, which frequently happens with the use of asynchronous resets and when they're used inappropriately. And also having to spend many hours of debugging your design if you use an asynchronous reset. So even though there are some caveats, we still strongly recommend that you build with synchronous resets. There are simply too many benefits. As an FYI, there have been cases where other synthesis tools will simplify the synthesis result so that it does not take as much advantage of the dedicated hardware when it determines that a design will be harder to meet timing. So it will basically infer very few shift register LUTs or block RAMs. So the design gets built out of additional LUTs and flip-flops to try and get as lean as possible, which can make it harder to meet timing. In this case, make sure your synthesis tool is inferring the appropriate resource, and if it isn't, instantiate the appropriate core into your design. Altering your HDL and design is the best way to infer a synchronous reset. Some synthesis tools even have switches to treat asynchronous resets as synchronous resets. Synthesis tools hate this option because their job is to build the functionality you describe, and you are refusing to build the necessary HDL code. But nonetheless, Simplify and XST support these switches, as do all high-end synthesis tools, and they are dangerous. Using these switches is not the same as manually changing your HDL code. However, the synthesis tools will put a register on a DSP slice or block RAM if it needs to be synchronous, but does not give the distinct optimization capabilities if the register was coded in the block RAM. So this option is not always complete, and do not expect this to be the same as changing your HDL. Keep in mind that if you don't code for a synchronous reset, in the future, another designer that works on your project will not know that you actually built with a synchronous reset. So keep in mind you may need to create a documentation trail. Also note that some believe that if the global set reset comes to the top of a port and disconnect the port, the optimization algorithms will rip out the reset. Unfortunately, it does not work that way. The synthesis algorithms do that optimization after they have chosen what resources are to be mapped. So you end up with a flip-flop that has an asynchronous reset. If you disconnect that port, remove it, or change it in some way, it does not necessarily change the implementation throughout the design. As you know, there are two kinds of resets possible: global and local resets. Global resets are used to put the FPGA into a known state. That is, with each flip-flop and block RAM output register, that means into a specific condition. You may also note that if this is done automatically by the FPGA as a normal part of the configuration process. In fact, if you do nothing, the FPGA defaults to resetting these resources to 0. It does not have to be coded into your design unless you want some resources to come out of reset as a logical 1. Well, we'll talk a bit more about this initialization during configuration a little later on. For most designers, a global reset is not necessary, but for some, especially ASIC designers, it is essential that they can emulate this behavior. To help give them access to this reset, Xilinx provides what's called a startup block for both Spartan-6 and Virtex-6. These components allow users to drive an input signal onto the global set reset net at any time and reinitialize the FPGA at any time. The benefit is that since there are so many resources that have to be connected to such a net, Xilinx has embedded this routing delay inside the silicon. This saves designers from having to route the signal on general interconnect and then consume valuable routing resources. Now, this resource cannot be inferred, so if you're going to be coding for a global reset in your design, you're actually coding a second reset. That is a huge waste of routing. So if you need a global reset, we encourage you to take advantage of the global set reset net and use it with the startup block. The other kind of reset is a local reset that is commonly part of any design. It, of course, only connects to just those synchronous elements that need it. Local resets are always routed on general interconnect like any other signal in your design. We have found that actually only some designers need a global reset in their design, especially since the FPGA automatically performs a global reset as part of the configuration process. But as I mentioned to many ASIC designers, this is essential for resetting their system extra times. So your way of resetting everything is with the startup component in that case. However, note that the performance of the GSR-net is relatively slow since it physically has to route to every synchronous element in the device. So don't reset it again unless you can tolerate a delay of around 3 clock cycles before everything gets reset. So just remember, the GSR is good for saving general routing resources by using the dedicated GSR, but it's slow. It is useful to understand that each flip-flop has the ability to have an init value associated with it. This initialization value is set after configuration and after any time the GSR-net becomes asserted. The init is often inferred by your synthesis tool if you assign an initial value in your HDL, and we'll talk a bit more about this later on. But that is different from the GSR. The GSR is an active high global reset functionality that is coupled with a dedicated routing resource for the signal's distribution. The GSR can also be used to restore the initial state of the flip-flops at any time. This is done with the init attribute. The output register of the shift register LUT, block RAMs, the DSP slices, can be initialized when the GSR is asserted in just the same way. But the memory contents of the shift register LUT and the memory contents of the block RAM resources will not be manipulated by the GSR. So as long as the device is not reconfigured, the contents of the shift register LUT and block RAMs will remain. You should also note that effectively the GSR-net and the local resets are ORed together on each flip-flop's reset input. This means that the flip-flop can get reset either with a global reset or a local reset, which is of course what designers expect. Now, as you can see from the startup block primitives shown here on the slide, the GSR is an input to the component, and as I mentioned, it is an active high input. To get the startup block, just instantiate the component as you see it here. Now, the instantiation shown here is limited by space, but for sample instantiations, refer to the Xilinx Unified Libraries Guide or use the Language Templates utility from the ISE software. This slide demonstrates what we mean by initialization and shows you how we recommend you code for it in your HDL. The set reset will cause the flip-flop to be set to the state inferred here. But note that inference is supported only for standard logic, bit vector, and bit data types. The integer data type cannot infer a reset. As you can see in this case, we're using the when others to define the state of each flip-flop in remaining conditions when it is not defined, and in our case, we care about the initial condition. Synthesis tools do react on this code. In this case, XST will place an init attribute of 0 on each flip-flop, which will assure that upon activation of the GSR, each flip-flop will go to 0. Most people assume that this is unsynthesizable code. It is synthesizable and it will affect the initial value of the register. But even more importantly for the customer, it means that when you do a functional simulation, you will have a known design. This is one of the biggest reasons that customers use for initializing their behavioral code. For example, if you do not do this and you have a counter, you will have X's counting plus 1, and all you will have is what's called an X counter. You will not have anything more than that, but if you use this with a counter or anything else, it will start with a known value. This is definitely a coding style you should be using, whether you're doing a set or reset. Now please note that what this means is that by using an FPGA, you get a free reset because the GSR is activated after configuration by default. If you want to control the reset state, you can with this example. This can be helpful if your design does not use any local resets. And as we shall see, if we remove the global resets from our design, we have an easier time getting the dedicated hardware inferred. You could still use a reset in your design if you wanted, but we might not bother in that case. And remember, if it simulates properly, it will function in your FPGA. You should remember that the shift register LUT does not have a reset port, so if you build a local reset into your design, you may create a problem for yourself. If you have a local reset on the shift register in your code, the synthesis tools are left with one of two choices. They either do not add the SRL primitive to your netlist, meaning they will use a bunch of regular CLB registers, which is not what you want because that will use a lot of flip-flops, or they can try to emulate the reset functionality. Now, emulating the reset means that they add more logic and the design becomes even slower than it should be in some timing critical cases. You should also note that the shift register LUT can easily be inferred when you build synchronous FIFOs, non-binary counters, terminal count logic, pattern generators, and reconfigurable lookup tables. So it's possible that you could infer more SRLs when you code without a global reset, and that of course will reduce your overall size of your design since you'll be saving registers. In one customer design, there was a global reset through everything, and the known shift registers could not be connected. They in fact were inferring 100 shift register LUTs and were doing a good job making good use of the dedicated hardware. But when the customer removed the global reset from their HDL, they obtained over 150 shift register LUTs. The customer obtained even more shift registers than were initially recognized. A common question is, can my synthesis tool emulate an asynchronous reset when using the SRL? The answer is yes, but currently only Simplify can infer its functionality. The caveat is that this adds logic to emulate the reset, which eliminates the benefit of using the SRL. Simplify can also add logic to emulate a synchronous or asynchronous reset when using the DSP slice resources, but this also kills some of the benefit of saving registers. Note that XST does not allow inference of the SRL when using a reset at all, so keep in mind that it's possible to build too much inference capability into a synthesis tool, and that you should always make sure you're inferring the dedicated hardware that you expect to get. Now note that this situation does not occur if you used a GSR. We're only really talking about the case when you're using a local reset. Meeting your timing objectives is a lot easier when your design does not have a global reset outside of the GSR. In fact, performance improves by an average of 18% compared to designs that do have an additional global reset. Now, this also speeds implementation time and requires less memory during implementation. So maybe instead of saying no resets, we should just say, be sure you use the GSR. In this slide, you can see how much fan-out any typical global reset can have when it's routed on general interconnect inside your FPGA. So this is not showing you a GSR example. This is probably the biggest reason to move resets from your design, since all of these routing resources will be available to you and the rest of your design to help meet critical timing and increase device utilization. This can be very, very important, since this will help timing critical paths greatly. This also gives the tools more routing flexibility and greater chances of you to be able to meet all of your timing needs. A common question we get is, can you migrate resets to the global routing resources? Recall, those are used for distribution of clocks. Well, the answer is yes, by instantiating a buff G and assigning the reset signal to a dedicated clock pin. But be aware of cryptic messages by the ISE software tools. That's the implementation tools. They will not recognize this as a wise use of the FPGA resources because they're designed to use clocks on the global routing resources. You should also be aware that the tools will not automatically move resets to these dedicated clock pins, that this must be done manually. If you're going to do this, try to plan on assigning this early, since it does affect the final pinout of the device. Note that in the past, the implementation tools would infer the GSR signal for true global set resets automatically. However, the implementation tools do not do this any longer, so you'll have to assign this manually. You should also keep in mind that the block RAM's clock enable functionality has precedence over a reset. With flip-flops, the reset has precedence over the clock enable. So if you use a clock enable and a reset together on a block RAM, you have to code for it properly, and it's different than the flip-flops reset and clock enable functionality. Other synthesis tools can insert bypass logic to prevent these kinds of mismatch errors. This is intended to force the memory's outputs to a known value when read and write operations occur in the same memory, so it's a good thing. Now, this will be changed in the next generation of Virtex products. This functionality is also in the Spartan devices, so if you don't code for a global reset, you don't have to worry about this. A common question we get is, how do I control my synthesis tool's ability to infer clock enables? Well, the answer is to code them only when needed. Recall that like synchronous resets, clock enables can be connected directly to the flip-flops or be connected to a LUT input. The reason we code only when they're needed is that you might want to design your lowest fan-out clock enables to use a LUT input. This can decrease the number of control sets in your design and give the tools a better chance to meet your timing objectives. So actually using a clock enable and controlling its use, whether it's to the clock enable port or to the LUT input, is nice flexibility and a very good thing to have. If a low fan-out clock enable is necessary in your design, use your synthesis tools attributes to control this. Do not use the global switch to turn off the use of clock enables. This can create big problems for you. To code for a local clock enable, we recommend you follow our suggestions you see here. So in this example, instead of coding it as we usually do, as seen on the left, which will force the clock enable to the register's clock enable port, instead, force the clock enable signal to be forced to a LUT input. Code it as part of the register's output, as we see here on the right-hand side. Write the detailed equations and the explicit connections to the register's output. In this case, by having more than one input, it forces the clock enable input to the LUT input. Now please note, Xilinx is not recommending you design asynchronously. Just what you try to reduce the designing low fan-out clock enable signals into your design, that is, clock enables that drive fewer than 8 registers. Synthesis tools will get smarter about when to use the dedicated clock enable control signals and when to move the clock enable to the data path, that is, to the LUT input, but it's going to take some time. You should also note that some synthesis tools allow the user to disable the use of the clock enable port on the register. Xilinx, again, does not recommend this, typically because on average it results in the use of 25% more LUTs and a waste of resources. While we're on the topic of the use of clock enables, don't forget that Virtex-6 and Spartan-6 have additional built-in clock enable resources. This is different than your register's clock enable port or using a LUT input. The buff-G clock enable and the buff-H clock enable primitives allow you to turn off a clock rather than distribute a high fan-out clock enable signal. Now these will have to be instantiated and work best when the logic connected to the clock enable is located in small regions, usually a single clock region. But their use will save routing resources, of course depending on the clock enable fan-out, and it's something that you should consider from the beginning. Under the category of other tips for getting the most out of Virtex-6 and Spartan-6 devices, we just wanted to make a note about building adder trees. Simply put, don't build them manually. That is because most designers build adder trees that makes larger adders in the last stages, which increases the number of logic levels, kills performance, uses more resources, and is slower. You're better off using adder chains, which obtain peak performance and use less power. This type of design requires additional pipelining, which adds latency but gets optimum performance when targeted toward the DSP slice resources. Now, the easiest way to build this is by instantiating the appropriate core from the core generator, which will build this optimized component automatically. This will allow you to get the most out of the DSP slice, save device resources, get better speed, and save power. And simply put, wow, that's just a whole lot of advantage. So make sure you do this. Since we've been talking about registers being a premium, we wanted to take a second and mention some considerations about synthesis options. First of all, don't over-constrain your design. This means that you should not place timing constraints on your design that are, first of all, unrealistic. As we always say, place timing constraints that reflect your timing needs. Remember that unless you are operating at worst-case operating conditions, you already have some slack. Over-constraining typically makes designs bigger and increases the number of registers used, since synthesis tools tend to replicate logic to decrease fan-out on timing-critical paths. Typically, this increases register usage by anywhere from 1 to 5%. Global optimization settings don't usually solve your register usage problems, although they can generate different results. Typically, global optimization can reduce your flip-flop usage by up to 10%. However, this often forces the synthesis tool to generate extra control sets and can result in unusable flip-flops. So, feel free to try it and compare results, but don't expect it to solve all of your problems. Finite state machine optimization can save you some flip-flops. This is because most finite state machine optimizations will use one-hot encoding, which uses more flip-flops in an effort to increase speed. With Virtex-6 FPGAs, the 6-input LUT means one-hot encoding is not quite as useful as it used to be with the 4-input LUT structure. I would recommend that you synthesize your finite state machine yourself by trying binary, one-hot encoding, and gray encoding and experimenting between. Then compare results and see which one you like best. It also is important to determine whether your finite state machine is part of a timing critical path, and often they are. If so, you may have little choice but to use one-hot encoding. But be an engineer and evaluate your encoding yourself. Note that over time, this is something synthesis tools will learn from and improve upon. Finally, don't use your slice or LUT compression switches. While this does not consume too many extra flip-flops, in some cases latch-throughs were used and consume extra registers. Recall that the slice does not allow you to separate the flip-flop from the LUT, so in the case of a latch-through, the LUT is used and the flip-flop ends up being wasted. Replicating high fan-out registers has always been recommended for FPGAs because it allows the duplicate logic to move closer to destinations and shorten routing delays to improve timing. However, manual duplication is easier because synthesis tools tend to not choose good names for the duplicate components. Likewise, allowing a synthesis tool to replicate until it is satisfied is not always as helpful as you might think. I have had many customers ask what maximum fan-out to set their synthesis tool. In fact, the choice of setting values depends on how far you are from meeting your timing objectives and do you have sufficient resources left available. So keep in mind that if you have a high fan-out secondary control signal you're generating, to try and anticipate the fan-out and duplicate the logic at least once. When you duplicate logic, don't forget to also name this duplicate logic appropriately. Specifically, use the same name followed by an underscore A or B. This will prevent the tools from seeing the logic as related as in a bus. By default, synthesis tools tend to duplicate logic and give it a number as in underscore 1 or underscore 2, and this forces the logic to be related and directs the implementation tools to keep it placed close together. So rename it A or B as I described. The retiming option allows the tools to move registers forward or backward in a data path. It is still recommended. The use of the ILB registers has always been to clock data in and off chip as fast as possible. However, no one has ever really talked about if it has any impact on internal performance. Well, it can, but it will depend on a few things. First of all, the pin assignments should be near the destination logic. If not, then there will be some internal net delay, and that can be a problem. But depending on the size of the die and the destination, this internal routing delay can become significantly large. So make sure your pin assignments are good. You might even consider making some area constraints to keep that source or destination logic relatively near the pins. If you decide that your input registers don't need the ILB registers, then the tools can disable the ILB register placement or usage. This will then allow a CLB register to be used, and the input time will have its delay increase as you would expect. So if you still need fast input or output times, you might want to stick with the ILB register, or even do it on an individual basis. To turn off the use of the IOB registers, globally disable it in your synthesis tool and in the mapper as shown in the screenshot from within the ISE tools and XST. Then, if you need some registers in the IOBs, you can use the UCF attribute placed on each individual register specifically. So let's take a minute now and review some of what we've learned in this recorded e-learning. Avoid asynchronous resets on block RAMs. That's because the block RAM's output register only supports asynchronous reset. Avoid asynchronous resets on DSP slice resources. Again, their flip-flops only support asynchronous reset. Note the use of IOB registers can make it more difficult to meet internal timing. So use the IOB registers when you're trying to improve your I/O timing. That's the clock to output time or your setup time on those input or output registers. Xilinx recommends not using synthesis options to convert asynchronous resets to synchronous resets. And we discussed that in a little bit of detail, and probably at this point you're not going to ever forget to do that. Continuing on with our summary, synthesis tools can move synchronous resets from control ports to the data path, and that's a good flexibility and a good reason to use synchronous reset coding rather than asynchronous reset coding. This allows you to reduce the number of control signals you might have. Continuing on with our summary, synthesis tools can move synchronous resets from control ports to the data path, and that's a good flexibility and a good reason to use synchronous reset coding rather than asynchronous reset coding. This allows you to reduce the number of control signals you might have, which allows the synthesis tool to minimize the control sets and allow different pieces of logic to be placed together in the same slice or into the same CLB. Avoid the use of global resets. Now specifically here, what we want to encourage you to use is the GSR, the Global Set Reset Net, whenever possible, which is used automatically and is used to reset the device and have the system come out into a known state after configuration. So anytime you can use the GSR, you use it. But if you're building an additional reset to reset all your flip-flops, don't do that. Try to use the GSR. If you need a global reset, use the startup block for either Virtex-6 or Spartan-6, and again, initialize that in your HDL. If you can remove a global reset, you will save a lot of routing, and this will give the tools more flexibility to meet all of your timing needs, often critical timing needs. And again, avoid resets on your shift register LUTs, specifically here since the shift register LUT has no reset functionality, unlike the DSP slice and the block RAM, which do have reset capability. So keep that in mind. If you can avoid using resets in your design, you're more likely to get many more shift register LUTs. There are some very useful resources available to you on support.xilinx.com. The Synthesis and Simulation Design Guide discusses some of these same topics. The XST User Guide is very helpful for example inferences of architectural resources. This is often what is most helpful to customers, so I strongly encourage you to check out both of these documents. Note that all the coding techniques that we discussed here apply to XST. If you want coding styles and attributes for another vendor's synthesis tool, they're kind of similar, but you'll have to go to their website to learn about their synthesis tool, or else go through their synthesis tools documentation. If you want to learn more about the various synthesis options available in XST, I recommend the Help menu. It's pretty helpful, but generally I still go with the defaults and only work with the options we recommend as part of the Designing for Performance course. Likewise, there is a Synthesis Options REL. You probably want to go look for that. To learn more about the startup block and other Xilinx primitives, check out the Libraries Guide. Now, please take a second and give us your feedback on this REL. All you have to do is click on the icon at the end of the recording and submit an evaluation. If you found this helpful, and I hope you did, it is important you take a couple minutes and tell us that. And that will help us to allocate the proper resources to maintain this kind of technical support. Finally, again, thanks for listening to this recorded e-learning on Virtex-6 and Spartan-6 HDL coding techniques, Part 2. Again, my name is Frank Nelson. Thanks for your time, thanks for your attention, and again, thanks for your business.